Good morning, here we are at the physics video lecture. Physics 105B video lecture 27. So let's begin. I have a really nice example today to apply just about everything we've done up until now. And so I'll just recapitulate some of our ingredients here. We know that we have the inertial tensor dm r squared delta ij minus xi xj integrated over the body. And out of this definition we find that for a flat body, the two of the principal axes, the sum of the two principal moments of inertia equal the third. Okay, so for a flat body, and without loss of generality, we'll say I sub 1 1 plus I sub 2 2. 3. So we're going to have a nice example of that. And we also have, in terms of the dynamics, we have L equals I omega. So that's the matrix times a vector. We have T equals 1/2 double sum I sub ij omega I omega j, and we can take that to mean that that's 1/2 L dot omega, which can be convenient. We'll use that today as well. And finally, very generally, maybe I'll leave all of these up, we have generally the time derivative of a vector is equal to its time derivative in the body frame plus omega cross A. So we're going to make use of all three of these ideas in a really interesting model that brings everything together. So let's start. Yeah, so what our model is the uniform disk of radius r. So uniform flat disk of radius r. Uniform flat disk, mass m, radius r. Let's go ahead and write it that way. And I'm going to want a bigger picture, but I'll start with this one right here. So we'll have our x, y, and z body axes, and our disk is in the xy plane. Okay. So the inertial tensor that we're going to use around the z-axis, of course, we know we have m over 2 r squared. And that means that the inertial moments around the x and y axes will be half of that each. So we'll have m over 4 r squared and m over 4 r squared, and then we have zeros everywhere else. So there's our inertial tensor for this uniform flat disk, mass m, radius r. And so far so good. So the next picture I'm going to make a little larger. So describe a scenario now. So we've got this self-same disk, and those are its body axes. Okay, let's see if we can draw this nicely. There we go, radius r. X, Y, and Z. And we're going to have it rotate about an axis that will lie in the YZ plane. Okay, so I have to draw this. Maybe I'll use another color. And the reason this is such a good example, and it'll go parallel, is we could actually build a model of this. If we have a flat cardboard disc and right through the middle, we stick a kebab skewer and then tilt it a bit, and then imagine twirling that object. Okay. Then if this blue vector, which is going to be the axis of rotation, if that were parallel with the z-axis, it would twirl very nicely. We could take this all the way down. Let's go ahead and call this alpha. We could take this all the way down to 90 degrees, and then we would be going around the y-axis would be our axis of rotation. So when alpha is 0, the z-axis is our axis of rotation. We tilt it all the way down to alpha equals pi, and then the y-axis is our axis of rotation. And it would be nice to build the model, but you can practically just think about it and feel what's going to happen. Okay, we've got a skewer through there, piece of cardboard. You guys may want to build one, and then you're twirling it around that axis. Good. So let me label some stuff. Okay, so so this is the vector omega, and it's a fixed axis, is the angular velocity vector. Okay? It's the angular velocity vector, but it's a physical model that we're actually thinking about here. Angular velocity vector, and omega is part of the YZ plane, and what's also interesting is it's fixed in the YZ plane, just by construction, but if I hold this thing and twirl it, it's also fixed in real space. So note, omega is fixed in the body system and the inertial system. Again, by construction, so we can inertial system. Okay, by construction here. So we have that. And we had a y-axis, x-axis. Recall, we had a theorem, d omega dt is equal to d prime omega dt. This one being the body system, this one being the inertial system, time derivative. So that's consistent with that fact. Let's see what else we have. So before I go any further with this, I'll just talk about the general case. If the body rotates about a principal axis, we could have actually talked about it up here because we have the inertial tensor. So if the body rotates about the principal axis, and we're looking at this right here, L, which is equal to I omega, is equal to, well, just point out what's going on then. If it rotates about a principal axis, then L equals I omega with omega equals omega times x I hat. Okay. in other words, if you do that matrix multiplication, you're always just going to get multiplication of this by corresponding component of the angular velocity vector. So L sub I would be equal to I sub I omega yeah, I'm going to put another I there. Okay, yeah, I have another way of writing that, so for L vector equals I sub I omega x sub I hat, where this is, you know, ijk or xyz hat. So that means L and omega are parallel. Okay, long story short. So if you're rotating about a principal axis, L and omega are parallel. Very important, because we remember from last time that's not generally the case. Okay. Generally, and this blue vector I've drawn here is not around the principal axis, and so L and omega will not be parallel. So what we're going to do next is construct what L and omega are doing in that case. So we'll always refer to this diagram up here, which I think I'll leave up on the board. And we're going to use these, but I have them here, so I need some space. I'm going to erase them. So now with those vectors as defined, let's go ahead and do this matrix multiplication. So we have up there so once again, I sub ij equals smaller, mr squared over 4, 0, mr squared over 4, and 0, 0, mr squared over 2. And what about the omega vector is given right here? Okay. We see we have 0x component because we're in the yz plane. So we have omega sine alpha and omega cos alpha for that vector. And now if we multiply this matrix times that vector, we get our angular momentum. So I omega, and it's going to have two components. Okay. But we're going to have 0 for the first row times first r squared. Pick off the first row, first column, and then second row times column, and third row times column. So yeah, first row times column is 0 times 0. Second row times the column, we get the mr squared over 4. So we get the mr squared over 4 omega sine alpha. And third row times the column, we get the mr squared over 2. Mr squared over 2 omega cos alpha. Okay, agreed. But the thing is, L and omega are clearly not parallel because they have these different coefficients. Okay, we have mr squared over 4 and mr squared over 2, where we just have a 1 and a 1. So we want to place this vector in that sketch there, you'll notice it's still in the YZ plane, but its Y component is shortened compared to its Z component if you compare it to that. So I'm going to draw that one in red on the same picture. And it will be somewhere here. The length depends on how these things are scaled, but there's the vector L. So just important to note, they're clearly not L and omega not parallel. Because the Y component shorter by a factor 2. And since they're not parallel, we're going to find that there's a torque. So I have those there. And in fact, let's look at this physically before we do any calculation. Because remember, omega is the vector that's constant in real space or in the lab frame and in the body frame. So as I twirl that thing, you just got to imagine twirling that thing. Then the blue vector is constant. That's what I'm holding between my hands. Those are those skewers, right? That's this ruler. And therefore, L, which is in the body system in the YZ plane, is going to be twirling around omega. So I may even indicate that with some kind of dotted line. So this L is going to be moving around kind of on a cone. That means L is definitely changing in time, and dl dt is a torque. Therefore, there's going to be a torque involved. So yeah, what I like about this model is you can stop and visualize everything that's going on. You actually build it and feel it if you want it to. Okay. So that's what we have so far. So we see from the model that L, although restricted to the YZ plane in the body, to the body YZ plane, L moves in the lab frame, or which in the inertial frame or the lab frame. And what do we know? We know that torque is the change of angular momentum with respect to time. So there's going to be a torque involved here. And how do we get that torque? Well, I erased the equation for the board here, but we know that's just going to be omega cross L, comma, because, and I'll just rewrite what we had, dA dt for any vector is d prime A omega cross A, right? The time derivative in the lab system versus in the body system. So we'll get that torque just by doing omega cross L. So that's our next task. This picture will keep up here. Okay. So torque is omega cross L. So torque is equal to, I'll just write them out here. So we have 0 omega sine alpha omega cos alpha, and I'm making the cross product with 0 mr squared over 4 omega sine alpha mr squared over 2 omega cos alpha. So that's clearly only going to have an x component. Okay. And that x component will be cross product this times this minus this here times this, so that's mr squared over 2 omega squared sine alpha cos alpha minus mr squared over 4 times the same thing. So I can actually just write that, not 0, 4 right away. So there's our vector, 0, 0, and that's the torque. So now again, let's go back to the model and see if this makes some sense. Well, first of all, omega cross L, just, you know, these two in this plane, they're going to be, as a cross product, perpendicular to that plane. So just, and you can even see the direction, geometrical direction has to come out the x-axis, so that's good. And so a torque around the x-axis is what is it's going to produce a wobble feeling. So if you actually build this model, this thing's going to have this wobble feeling to it as you twirl it. Okay, that's the torque that you're feeling. This is about the x-axis in the body system, and of course the body, this x-axis is spinning around in space in the lab frame. Okay, so there's that. We have the torque. One more thing I want to do. The number of things. So again, back to our feeling for the physical model. What happens when alpha is equal to 0? Alpha is equal to 0, we're twirling it right around the z-axis, and sine of 0, 0, the torque vanishes. So that's the smooth non-wobble. And alpha equals pi over 2. Cosine pi over 2 is 0. That would mean we're spinning it around this axis here, and again, we're not going to have that wobble because omega and L will be parallel in those cases. So then torque equals 0. Okay. So we have that. I want to do one more calculation, picture up there, and that's the kinetic energy. Kinetic energy of this object that we're spinning. So I can leave this up. So we'll write here, finally, kinetic energy. And we'll go ahead and calculate it this way. T is equal to 1/2 L dot omega, as I wrote up there earlier. So we've got the 1/2, and we have L and omega up here. Yeah, this was L cross omega, and now it's L dot omega. This is omega cross L. So we just take the dot product of those, and we have so we're gonna have cosine squared. So let's go ahead. So we have m r squared over 2 omega squared, and then we'll have a cosine squared plus 2 sine squared. So over 4. We'll do it the other way. We'll do mr squared over 4. Mr squared over 4, omega squared sine squared alpha. And then we'll have twice as much there, so 2 cosine squared alpha. And this will simplify. Okay, yeah, 1/2 mr squared over 4 omega squared. So I'm taking the cosine, I'm keeping the cosine squared, so I'll have 1 plus cosine squared alpha. 1 minus cosine squared alpha sine squared plus 2 cosine squared alpha. Good. So the kinetic energy finally, T is equal to 1/2 mr squared over 4 omega squared 1 plus cosine squared alpha. And again, we have the model up there, so let's make sure this makes some sense. So when alpha is equal to 0, okay, when alpha is equal to 0, we have 1 plus 1 is 2, and 2/4 is 1/2, and it's the kinetic energy of spinning around the z-axis as it's supposed to be. If alpha is pi over 2, then of course there's a 0 there, and it's the kinetic energy of spinning around the y-axis. Okay, half that kinetic energy. Good, so this is okay as well. All right, that's about all I had, because I think this is a nice self-contained little exercise. Check the time here. Yeah, I've also often thought a nice project would be to build one of these, but it would get complicated. Probably best to take a skewer and a circular disc and play around with that a bit. But yeah, if you wanted to get fancy, you would carefully tape some coordinate system straws on it, or not tape, but glue. But if you had the coordinate system sticking up this side, then you'd have to balance it with one on the bottom and so forth. So you're going to get into a little more interesting stuff before you know it. Okay. Yeah. So I'm going to leave it at that. This is a really rich system, actually, so you can go through everything we did here and make sure you see it. And you can even build the thing and twirl around a bit. And it exemplifies just about everything we've talked about. You have to make use of some properties of the inertial tensor. We saw the properties of that D, it's not up here anymore, of the time derivative of the vector in the body versus the lab frame and so forth. Property of a laminar body having this kind of inertial tensor. Constancy of omega in both frames, in the body frame and the lab frame. Yeah. Okay, good. So next time we're going to talk about, well, I'll just announce it, we're going to work our way up into what are called the Euler Equations. Euler was everywhere in math and physics, so Euler has more than one set of equations. The Euler Equations for the rigid body, that's what we'll do next time.